Good afternoon, ladies and gentlemen. My name is Kevin Lee. I'm a technical program manager at Facebook, and today I'm here to talk to you about Big Sur. So Big Sur is our purposely built hardware for AI applications at scale. So our data center is currently filled with servers, storage systems, and network appliances. To add to this, we are adding some massively parallel machines. Although these machines, although AI and machine learning has been around for decades, the advances of AI has been largely in step with hardware and the technology that has been driving hardware. So at Facebook, we have made great progress so far in using off-the-shelf equipment and infrastructure design, and we've developed software that can read stories, answer questions about scenes, play games, and even learn unspecified tasks. But we realized that by truly tackling these problems at scale would require us to design our own hardware. So Big Sur is our next generation GPU-based hardware for training neural networks. So Big Sur. So a few design points of Big Sur is that it supports up to 8 PCIe Gen 3 full height dual slot cards. It's designed to support standard SSI EEB compliant motherboards. It can host up to 300 watts of acceleration cards, and they are OpenRack compatible, and it is a 4OU chassis with 2OU for rails for serviceability. So I'll talk to a little bit more about this as I go on. So the architecture of Big Sur comprises of 3 major areas. There is the motherboard, the linking board, and the hard drive or SSD backplane. So the motherboard, as I mentioned, you can use off-the-shelf standard motherboards for this. And then they are all connected to the linking board. The linking board is where you put these accelerator cards, such as NVIDIA's GPUs, on top of them. And then there is a SSD and hard drive backplane that houses up to 8 SSDs. So the cool thing about this design is that actually all these things are flexible. So they're all organized using cables, and you're able to move the PCIe topologies according to what application you're using, such as if you want to use it for oil and mining, or if you want to use it for AI applications. And I'll go through that in my next slides. So Big Sur is modular. They support many different accelerator cards. It was designed around the NVIDIA M40, as shown in the picture here. But they can also support the AMD FirePro cards, the Intel PHYs, and also any other sort of FPGAs, such as the Mellanox CX4s. So again, the motherboard, you can see it here in the picture. It's a 12 by 13-inch motherboard, compliant motherboard. So with the right PCIe connectors, you can put in any sort of motherboard that you like. They are OpenRack compatible. So this is an actual picture of 3 racks in our data center of the Big Sur systems. In the Facebook data center themselves, we have limitations in power, so we populate around 4 Big Surs per rack. It is flexible in topology. We're able to utilize the GPU direct from NVIDIA to utilize the direct memory access and direct memory transfers across all GPUs. So there are different types of topologies, and I'll really quickly go through this. So there is a balance config. This is the config that most OEM vendors are using. The communication from GPU 0 to GPU 1 is the fastest. But you can see later on that the communication from GPU 0 to GPU 7 is very slow because it has to go through the QPI link. So what we did is with the Big Sur, you can move around the cables. So you're able to do the common config and also the cascaded config. And the cascaded config is the best in our opinion on AI, because all GPUs are situating on the same CPU root complex. So we also looked into different topologies for the network cards to support RDMA or InfiniBand. So again, we can move the NICs around. We can put the NICs on one CPU or put them across the PLX chips so that they can share all GPUs. So again, the common config, this is another config that many of the HPC companies configure to. In the cascaded config, what we're able to do is we're able to move the NIC from the CPU over to the PLX chip, and then with that design, we're able to couple many of these systems together to create one big platform and share direct memory access across all of the systems. So I'll go through a few quick design methodologies that we went through. We were really concerned about serviceability, thermal efficiency, and of course performance. So on the serviceability side, these are a few things that I picked out that we did to make it more serviceable. We have hot swappable fans in the back, so you can actually pull the whole server out on rails and service it from the front, or you can go to the back or the hot aisle at Facebook and service the fans. We also enabled to be able to use thumb screws to remove the GPUs themselves, so swapping a GPU can be within seconds. We have the cables, of course, for the PCIe topology. We have removable trays, rails for in-rack servicing. We have the 2.5-inch drive carriers in the front, and also, yeah. So on the thermal efficiency point of view, again, we have the four 92mm fans at the back. We place all the GPUs in series so that they can be, they don't have preheat and they can cool efficiently. We optimize the air duct at front so that we know that the GPUs at back can pull up to 300 watts while the motherboard is up to 380 watts. So we optimize the air duct for this, and we also increase the U height of the server itself so that we have enough space for airflow, and that's through a 4.0U chassis. On a performance perspective, we saw that by using this type of topology, we ran the NVIDIA bidirectional peer-to-peer test, and we were able to see that we get 25 gigabyte per second of bandwidth across from GPU to GPU, and we are able to have low latency around 6 or 7 microseconds. So thank you. I have a workshop tomorrow if you guys want to have questions or want more details of the design. Thanks.